thank you all for joining this session. And we had a great part one of this course. Originally, the idea was to do only one part, but then as we started doing the course, we started realizing that there is more content to cover, and we cannot cover it in one part. So we kind of decided to split it into two parts. We successfully completed the first part of this course, which was titled as Technology Fundamentals Basics. And we covered a lot of ground there. We had about 16 sessions. Each session is 1 hour long, and as Sainath mentioned, we conducted an exam at the end, and now we are on to the session 2. And we were able to do this because of all the support and energy that we got from all the attendees. And there were many people who attended these sessions, even though you're very busy with your work. Some people have this is working time for them, but still they took the time to attend these sessions, and we really want to thank you for all the energy and all the attention that was given to this course. So hopefully you found this the first part of this course useful. If you have not attended the first part, of course you can go back and watch all the videos on our website. And then today we are on to the second part. So before we get into the second part of the course, I just want to quickly summarize what we covered on the first part. The first part, we did it in 4 modules. Each module had 4 sessions. Each session was 1 hour long. So the first module covered basics of Wi-Fi, introduction, the evolution of Wi-Fi, the history of the technology, how the technology evolved in various generations, and so on, and the various applications of Wi-Fi. And then we also looked at the various network topologies, and basically how Wi-Fi is deployed in homes, in enterprises, in different types of modes, mesh modes, infrastructure modes, and so on. Then we talked about the wireless LAN standardization process, which is very important, because as the technology started evolving, people started realizing that to really scale this technology, it has to be standardized. And there were standards bodies, IEEE, and so on, that really helped in standardizing Wi-Fi. And we talked about how the standardization process works, task groups, working groups, how all of that works. We talked about that. And then we also talked about basic functional building blocks of a Wi-Fi router. That's mostly what we covered as an overview of Wi-Fi technology in module 1. And then module 2 went into the details of the wireless LAN physical layer. For those of you who understand Wi-Fi technology, the 2 main layers in Wi-Fi that are mostly used are physical layer and MAC layer. That's where most of the Wi-Fi technology resides, because Wi-Fi for the most part is the last hop. Basically, it's just the edge technology. So edge technology is normally dealing with physical layer and the medium access layer, right? So we went into detail on wireless LAN physical layer in module 2. We talked about how frequency allocation works in Wi-Fi, how the unlicensed spectrum works, ISM bands, unibands. We touched upon 6 gigahertz bands and so on. We talked about basics of how signal propagation works. What is a signal? How does it propagate? How does energy propagate? What is how signals are measured? How electromagnetic waveforms work, and units and things like that. We talked about that. And then we went into basics of modulation and coding, and we talked about MIMO, multipath. We talked about spectral efficiency, different types of digital modulation techniques, amplitude modulation, frequency modulation, phase modulation, and so on. Then we went into the famous MCS table. We looked at the MCS table in detail. We talked about how the MCS table is structured, what are the various things that basically parameters that are used in the MCS table to get the different PHY data rates. We talked about the modulation rates, coding rates, channel bandwidth, MIMO type, and number of other things that contribute to creating the MCS table. And then we talked about the physical layer headers, the key functions, the PLCP layer, the PMD sublayer, and so on. In module 3, we went into the MAC layer features. Here we talked about basics of the MAC layer, how the management functions work, control functions work, and how the data plane works. So since a wireless LAN access point is supposed to manage a Wi-Fi network, there is a management plane. And there are lots of functions of the management plane, things like beaconing, scanning, and things like that. What is a basic service set? And what are the details around that? We talked about that. We talked about MAC framing, MAC headers, key functions of MAC headers. And then we also went into detail on how carrier sensing and medium access work. So one of the fundamental problems in Wi-Fi is there is an access point, and there are multiple devices that are trying to connect to an access point and send information. So that is multiple access. So there are multiple people trying to access the same shared medium. right? So how do you make sure that works well without any collisions? And so that's all about carrier sensing, medium access. We went into detail about physical carrier sensing, virtual carrier sensing, signal detect, energy detect, and we talked about how random backoff works, how collision avoidance works, interframe spaces works, how QoS works, and so on. And then we also talked about data transfer, aggregation. How do you use the medium better by avoiding overhead? We said things like about 90% of the medium goes for overhead because it takes so many different types of frames to manage the network. So to reduce the overhead, there is this concept of aggregation where you can actually send a burst of data frames and you utilize your medium better. So we talked about aggregation and the different ways you can utilize the medium better. So we covered all of those things in module 3. And then the fourth module was about security and Wi-Fi. So we went into detail about from the very basics, the very basic security protocols like web. We talked about WPA, WPA2, WPA3, enterprise, captive portal, WPS, and many other things. And we also explained the basics of how authentication and encryption works, the various EAP methods, different types of .1x mechanisms, and so on. And then there was one session, interesting session, on how attacks and vulnerabilities happen in Wi-Fi, the different types of attacks we can see, man-in-the-middle attacks, and we talked about denial of service attacks and flood attacks and things like that, evil twin attack, and how you can actually mitigate these attacks by improving security. We talked about protected management frames and so on. And then the very last session, we covered seamless connectivity, roaming methods between Wi-Fi and cellular, and the secure way of moving from Wi-Fi to cellular and between different networks within Wi-Fi. We covered that in a fair amount of detail. So that was the 16 hours of material that was covered in the first part of this training session. Of course, we didn't cover a lot of things in the first part. We didn't touch upon OFDMA, multi-user MIMO, Wi-Fi 6, Wi-Fi 6E, Wi-Fi 7, and lots of other things we could not cover in the first part. And that is what we're going to cover in the second part now. Now, at the end, we conducted an exam, and we actually conducted 2 exams. And we were very happy to note that about 160 people attended these exams, which was very nice to see. And of them, about close to 110 people got certificates based on the score that they received. Some got excellence, some got merit certificates, and some got participation certificates. And we issued certificates to everyone, and hope whoever got the certificates are finding them useful, and you also hopefully learned some things in the sessions. Okay, so what are we going to talk in part 2, which I'm referring to as technology fundamentals advanced section. So whatever we are not able to cover in part 1, we are going to cover here. So first module, which is module 5, is going to have some of the features, the core features that we were not able to address in part 1. So we're going to talk about some of the standard extensions. In today's session, we'll talk about RRM, DFS, and fast roaming and things like that. And the remaining sessions in this module, we're going to cover the advanced features like Wi-Fi 6 introduced a number of other things like OFDMA, multi-user MIMO, BSS coloring, WPA3, and so on. And then we have Wi-Fi 6E that introduces the 6 gigahertz spectrum, 320 megahertz channels, and then AFC, and which is all very interesting technology. So we're going to talk about those things in detail, and then we're going to touch upon Wi-Fi 7. There's one session on Wi-Fi 7 that's going to talk about MLO and preamble puncturing and other new features that we have as a part of Wi-Fi 7. So in module 5, by the end of module 5, we should be covering most of the things that we wanted to cover from a technology point of view of basically Wi-Fi protocols, right? So that's what up to module 5, Wi-Fi protocols and basics of Wi-Fi technology. And then module 6, then I wanted to go a little bit onto the business side, because I like to also address the business side of any technology. So here we are going to talk about some more advanced use cases. And so we're going to talk about the various architectures of access points, thick APs, thin APs, models, and things like that, how that evolved over a period of time, and the different controller architectures, physical controllers, cloud controllers, artificial intelligence based controllers, and so on. So we're going to talk about that in one session. There's going to be one session on smart Wi-Fi features, how traffic shaping, traffic policing, parental controls, AI, ML, artificial intelligence features, analytics, advanced analytics features work in case of Wi-Fi. And what are those use cases? We're going to talk about that. And then there's one session on mesh, which is again a special case for Wi-Fi, mesh and multi-dweller unit scenarios that are used both in residential and enterprise environments. The various deployment models for mesh, how mesh access works, backhaul, how mesh roaming works, and so on. We're going to talk about that. And then there's going to be one session on Wi-Fi monetization. I think this is a quite interesting topic. May not be that interesting for the hardcore technical people, but for the people who are figuring out how Wi-Fi can be widely adopted, monetization has always been a big topic. Cellular networks have always had a way to make money, and Wi-Fi was always struggling to make money as a technology. But there are many ways in which Wi-Fi makes money, right? We all say that internet is free, but everything around the internet costs a lot of things, and everything around the internet makes money. Similarly, Wi-Fi may be free, but it actually enables so many other things around it in an enterprise. And what are the different use cases, how Wi-Fi can be monetized, how you can actually use Wi-Fi for optimizing your business operations in an enterprise network, how information technology has evolved into operational technology in enterprises. So we're going to talk about that in that session. That'll be quite interesting. So then module 7, it will change direction a little bit, and we'll come back to the technical side. And here we are going to talk about tools and troubleshooting. So now that you learned the basics of the technology up to module 5, how various aspects, how protocol extensions, how the medium access, how all these things work, we also need to understand tools, right? And this is mostly for the engineers who are participating. This could be test engineers, dev engineers. This could be people who are deploying Wi-Fi. This module is going to cover troubleshooting and tools. How do you use Wireshark more effectively? How do you have different types of Wireshark filters? And how does in different analysis you can do using Wireshark, advanced analysis, and so on. So we're going to have one session on that. And then we're also going to talk about different types of tools that are available, mostly free tools. We're not doing this for commercial reasons. So we're not going to talk about our product essentially. We might use our products here or there to demonstrate concepts, but we're not trying to use this as a way to market our product. So mostly we are going to talk about free tools that are available that people can use, like Wi-Fi scanner tools, Kali Linux tools, site survey tools, heat mapper tools that are freely available, open source tools that are available that can be used for advanced debugging and analysis. And then we are going to get into a little bit more details on the dev side, maybe into supplicant logs, AP logs, how AP debugging commands work, how the different types of APIs works when you actually try to access an access point, REST APIs, serial-based, telnet-based APIs, how to access debug logs, how to issue commands to access points. Again, we'll try to keep it generic. Every vendor has different ways in which they do that, but we'll try to use some examples, generic examples to demonstrate that. And then there was one request for OpenWRT last time. And so we'll try to do a session on OpenWRT to explain the basics and so on. We might invite someone from the industry as a guest speaker who is more expert in that area, but we'll try to cover that also in module 7. And then the last module, module 8, is going more into the testing side. So this is most for the tester. This is also kind of our personal area of expertise. We have been doing, I personally have been in the testing space for the last 20 years. So, and there are defining test methodologies, how to approach Wi-Fi testing for testing in the lab, right? And this is mostly for the Wi-Fi test engineers who are part of various organizations, who are working in companies that are building access points, companies that are service providers that are deploying access points, and so on. This is mostly for the test engineers. So we're going to talk about Wi-Fi testing fundamentals, basic approaches for Wi-Fi testing, for testing in the lab, in the field. And then the different types of testing you can do, how to start from basic benchmarking to how to do automation, how to do repeatable testing, and what are the different types of testing you can do, and so on. And then we're going to talk about different approaches of how to test in real environments, in test houses. What are the challenges there? How do you solve those challenges? And how do you come up with interesting ways in testing in test houses, different kinds of interesting test cases, and so on. We're going to talk about that. And then we'll also talk about test plan development. How do you approach in creating a test plan for Wi-Fi? So that's what we want to cover in module 4. Again, we are not going to try and advertise our products or anything. That's not the goal of this thing. It is completely neutral. And we will use certain products once in a while to demonstrate concepts. But the idea is to really impart knowledge here more than anything else. So hopefully that gives you a good overview of what module this part 2 is going to cover. For those of you who have not been part of part 1, everything is now fully up on the website. So if you go to our website, you can go to this link, and then all the details about part 1 are here. And for all the sessions, we have slides, videos, quiz, Q&A, notes. Everything is fully updated for all 4 modules. So anyone who has not attended the previous sessions can go back and can watch these at your own pace. And then part 2 is also kind of listed here. And as we create the content, we'll update it here as well. Okay, so now with that long introduction, so hopefully let's jump into today's session. Today's session is going to cover some of the kind of topics that we missed in the part 1. So just to kind of just summarize some of the topics, right? So we talked about Wi-Fi standards, .11 standards, and Wi-Fi standards started with the basic 802.11, which was around 1997 timeframe, 1 and 2 Mbps data rates, and then it evolved, and we started adding every time there is a new use case, a new problem to solve, we kept adding standard extensions. So this is how Wi-Fi came to Wi-Fi 6, Wi-Fi 7 now. So it was originally .11, then we had ABG, then we had 11N, then we had 11AC, which is very high throughput, and then we had 11AX, which is HE or high efficiency Wi-Fi, and we have 11BE now. That is now referred to as Wi-Fi 7. So these are kind of the main standard kind of milestones in the Wi-Fi world. But within these main standard milestones, in the between, there have been a number of standard extensions that are solving very specific problems, right? So in the case of Wi-Fi, we had a QoS problem. Initially, when Wi-Fi protocols were designed, people did not really think about QoS, and they didn't really think QoS was important, because the initial idea of Wi-Fi was it was supposed to be used as a best effort technology for doing email and maybe basic browsing and so on. But when people started doing voice and real-time video and things like that on top of Wi-Fi, QoS became very important. So then we had a standard extension 11E. We talked about that quite a bit. As Wi-Fi evolved in enterprises, security became a big problem. So enhanced security was important. 11I came along. We talked about that, right? We talked about 11U in the last session, where we talked about how you can successfully, seamlessly move between multiple networks, Wi-Fi networks, and between Wi-Fi and cellular. And that was a use case that was important. And so there were standard extensions there. We talked about how to protect management frames to avoid denial of service attacks and flooding attacks. So we talked about 11W. So like this, there were several protocol extensions that came along to solve different problems that came into place as Wi-Fi started evolving from the very residential technology to a widely adopted large-scale enterprise technology. So today we are going to talk about 4 such use cases that we did not cover last time. There is 11H, 11K, 11R, and 11V, and all of them are all standard extensions that are solving specific problems. And what are those problems and how do we solve them is what we are going to talk about in the next 40 minutes or so. Okay, so challenges from large-scale Wi-Fi adoption in enterprise. Okay, so as I said, initially the original standard did not really envision large-scale deployments of Wi-Fi, but it happened, and Wi-Fi started getting deployed in a large scale. When you do high-density deployments, what that means is in a small amount of space, you have lots of access points that are deployed, and we have to remember that the number of frequency channels that are available is limited. Right, so we don't have unlimited spectrum, unlimited bandwidth. So which means that when you're installing several APs in one location to increase your capacity, you have to do better frequency planning, and you have to make sure you use the channel allocation properly. And this is one of the biggest things that most people who are deploying Wi-Fi, they know this technology term very well, channel planning, right? They have to do channel planning very well to actually get optimal performance of the Wi-Fi network. And there are so many tools that do channel planning and so on, right? But one of the problems is how do you actually do radio resource management? Meaning all these access points are there, and each access point has many radios, and they're all using different frequency channels. So how do you manage the radio resource, basically using of all these radio resources? And how do you manage them effectively? is a problem that needs to be solved. The base standard doesn't really address that problem. And so to some extent, 11K was one of the standard extensions that came along that was trying to address this problem, right? We're going to talk about that today. And then, of course, as the 5 gigahertz spectrum opened up, there were more channels that opened up in 5 gigahertz, right? And some of those channels are used for other forms of communication, like radar communication. So at one point, the government agency said, government organization said, we are going to open up these channels that are currently used by weather radar and air traffic control and other types of communication mechanisms. They're used for those channels are used there, but they're not used all the time. So which means that we can open that up for unlicensed use. But the requirement is whenever there is actually a radar signal on any of these channels, you are supposed to get off the channel, and you have to prove to me that you are going to get off the channel when you see a radar signal. Only if you can prove to me that you can do that, then only you can use these channels, is basically what the requirement is. So there are a number of channels that are opened up there, and so the access point vendor has a choice. Either they choose not to use the DFS channels at all, or if they use the DFS channels, then they have to pass a certification that proves that they can indeed detect these radar pulses and move off of the channel. So then there was a standard extension there that basically looked at DFS and transmit power control, and that was what was referred to as the 11H standard extension. And then mobility continued to become a bigger and bigger problem. So as mobility, as people started doing delay sensitive applications in an enterprise network, and as enterprise networks started to have more and more access points, it is very common for a user to have a phone call or a Zoom call or something and walk from one place in the office to another place in the office. And when you are moving from one location to the other location, you are most likely handing off from one access point to the other access point. While that is, if you are doing basic data transmission, and that's okay to actually take time to hand off. But if you're doing a voice call, that handoff has to happen very quickly, and it has to happen in a secure fashion. So we need some form of fast but still secure roaming method, right? And that's where 11R came along, right? And then similarly, we have another issue that we need to solve is when clients roam, right? These clients can be very sticky sometimes. Some clients can misbehave. So for example, if I'm connected to an access point in this room and I'm getting very good signal, and as I move away from the current access point, my signal strength might be very low from the current AP, and I might have a much better signal from a different access point. But if my client is not good at roaming and it's very sticky, then it will not roam. It will just stay connected to the previous access point, and that causes a lot of inefficiencies in the network use. So then how do you solve the problem, right? Because it's the responsibility of the client to roam, and if it's not doing it, then it's a problem. To solve that problem, they came up with this extension for wireless network management, where the network can manage the client and it can tell the client what to do, right? So from that we got the 11B standard extension. So basically all of these are real problems, and these standard extensions try to solve the problem. Okay, so we're going to talk about each one of them in the coming slides. So first, DFS. As I mentioned, DFS is a basically channel allocation scheme that the idea here is you can use the radar, the channels on which radar signals operate, but as long as you comply to certain requirements. And so what this means is anytime an access point wants to operate on one of the channels that is used by radar communication, it has to first go and check and scan on the channel for a certain amount of time to make sure that there are no radar signals on that channel for a certain amount of time. This is referred to as channel availability check time, or what we refer to as CAT time, right? And once it makes sure that the channel is clear for a certain amount of time, there are no radar signals, then the AP can put itself on that channel, and it can start sending out beacons. And then let's say some clients come and associate with that access point, and then now you're sending traffic. Let's say after a certain amount of time, there was a radar event. Maybe someone sent a radar signal. This AP should then be able to detect that radar in real time, right? And as soon as it detects a radar, it should be able to, first of all, detect the radar successfully, and then it should be able to say, okay, now I detected the radar, I cannot operate on this channel anymore because there is a radar signal. So then the AP should be able to inform all the clients that are connected to it that it is actually moving to a different channel, and then it has to go now scan on a new channel to make sure if it is going to use a radar DFS channel, then it has to do the same process again. It has to go to the new channel, make sure that there is no radar signal on that channel for a certain amount of time, and then basically set itself on the channel and start beaconing, right? And so these are all the requirements as a part of the standard. So you need to check the channel for a certain amount of time. You need to be able to successfully detect the radar, and as soon as you detect the radar, you need to move off the channel, and you need to stay off the channel for a certain amount of time, which is called as the non-occupancy period, right? So these are all part of the testing requirements, and as long as the APs meet those requirements, they are allowed to operate on these channels. So the table here shows some details about minimum amount of time you need to check the channel to see if it's free. It's called the CAC time. There's also a non-occupancy period. So once you move off of the current channel, you cannot come back to that channel for the next at least 30 minutes, right? So there is a non-occupancy period, right? So these are all part of the DFS requirements. We are running short of time, so I mean I don't have a chance to go into a lot of detail, but this one topic could be like a 30-40 minute presentation if you go into all the details. So how is DFS actually implemented? So what is the AP supposed to do and what is the client supposed to do? So the AP is supposed to be able to detect different types of radar pulses when it sees a radar event on a channel on which on one of the DFS channels. So it should be able to first detect it, and once it detects it, it should be able to send something out as something which we refer to as a channel switch announcement message, which is a broadcast message that the device sends to all the clients saying that I am going to switch to a different channel, and it has to inform the devices which channel it's going to move to, and then basically the AP can move. And the channel switch announcement is normally sent either in the beacon frames or also in a special action frame, which has the channel switch announcement information element in it, right? And that's what the AP is supposed to do. What is the client supposed to do? What the client is supposed to do is anytime it is doing any active scanning, it is not allowed to scan on DFS channels unless it sees a AP that is beaconing on the channel. So what that means is, if there is an AP that is actively beaconing on a DFS channel, that means the AP has already done its job. It has made sure that there are no radar signals on that channel. Only then it starts beaconing. So now the client can say, okay, there is an AP that is beaconing on this channel, which means that there are no radar signals, so I can scan, right? But if it's not seeing any active AP beaconing on the channel, then the client has to assume that there might be some radar activity. And so it should not be actually sending any active scanning. It should not be sending any probes or anything like that, because those could interfere with the radar signals, right? So that's one requirement. The other requirement is the client can choose to stay connected with the current AP and move along with the AP to the new channel, or it can move to a new BSS when it sees the radar signal, right? Or when the AP says that there's a radar signal. So those are the requirements on the AP and the client side. If you look at a channel switch announcement frame, which is on the bottom of the slide, it has all this information. When the AP sends the channel switch announcement, it will basically tell what new channel that the AP is moving to, and it also has something called as a channel switch count. In this case, it shows channel switch count as 2 at the bottom right hand corner here. So what this means is that how many more beacons are you going to expect from you can expect from the AP before the AP moves to the new channel. So here it says 2, which means that the AP is going to send 2 more beacons, which means that it will stay on this channel for 2 more beacon intervals, and then it's going to move to the new channel when this count goes to 0, right? So this helps the client decide, okay, this AP is now leaving, so now I need to find some other AP to connect to, or I just need to follow this access point, right? And that's how the DFS implementation works. As far as making sure that the APs are following these rules, it is important to make sure that the APs are following these rules. And so there are certification bodies, and in every country has their own governing bodies that are making sure, regulatory bodies that are making sure that we are following the rules. In the US, you have the FCC, the Federal Communications Commission, and then you have in Europe, you have HC, and there are other countries that have other bodies, that regulatory bodies that regulate these things. So what do? They actually create a test plan, and there is a test procedure that you need to follow, and you need to pass the test. So every time you are making a new access point, or you are creating a new model of an access point, or you have a new major release of firmware or something, you have to take this AP to the certification body, and then you have to make sure that this passes the DFS certification. Okay, so there are many tests in the DFS certification. The most important ones are the detection probability test and the detection bandwidth test. So the detection probability test, what it does is it tests if the AP can actually detect the many different types of radar pulses. So one of the things to note here is there are so many different types of radar pulses that are used for various applications. Some of them are what we refer to as short pulse radar waveforms. Some of them are long pulse radar waveforms. Some of them are doing chirping. Some of them doing frequency hopping. There are many different types of radar pulses. Under FCC, there are 6 types of radars, right? So when you are trying to pass a certification, the AP needs to be able to detect all these different types of radar pulses. So the detection probability test will say, okay, type 1, I'm going to run 30 trials, and which means I'm going to generate 30 different types of radar pulses that fall under type 1, and the AP needs to be able to detect at least 60% of those to pass the test. So which means that out of 30, it has to detect at least 18 radar pulses, right? And if it successfully detects the radar pulses, then it passes that type. Similarly, it has to run type 1, type 2, type 3, type 4, type 5, type 6, and all of them have to pass. And then you pass the detection probability test. Similarly, there is the detection bandwidth test, which is where you need to make sure that the radar is, let's say you're operating in a 40 megahertz or 80 megahertz or 160 megahertz channel. So your 160 megahertz channel is wide. It covers an entire bunch of frequencies. But your radar event could happen anywhere here, because a radar signal could be narrowband. So it actually can send a radar signal at this point or this point, anywhere within this band. So you need to make sure that your AP is able to detect the radar signal no matter where that signal is coming in, whatever frequency it is coming within the entire band, right? And that is called the detection probability test. The detection bandwidth test. So within this entire bandwidth, at any point, if there is a radar event at any frequency within this bandwidth, you should be able to successfully detect the radar. And the requirement as far as that spec goes is if you have 160 megahertz channel width, at least for 90% of that channel, radar event could happen anywhere in any of these frequencies. You should be able to detect it successfully, and then you pass the test. So there's the detection probability test, detection bandwidth test, and then there are other timing tests that you need to pass to actually get the DFS certification. It's pretty involved and pretty complex, and we will put some references for you to go through that as well. Okay, so now let's jump into 11K VR and what are those standard extensions. So before we go there, we need to talk about roaming, right? Most of these standard extensions are trying to solve the roaming problem, right? So what is the standard roaming problem? You're connected to AP1 and you move from AP1 to AP2 and you need to roam. So normally in Wi-Fi, the traditional method of roaming is using a method called break before you make, which means that you break the connection with the current AP, and which means you disconnect or dissociate with the current AP, and then you scan, and then you move, and then connect to the new AP, right? And that could create a lot of delay based on what type of connection you have. If it's an open authentication, that could happen very fast. But if you're using server-based security, if you're using .1x authentication, you have to generate, you have to exchange certificates, you have to generate 4-way handshake. That process could take hundreds of milliseconds. Now, if you're doing email, then it's okay. Hundreds of milliseconds of latency is not a problem. But if you're doing real-time voice or video, then that could be a problem. Right? So the traditional roaming method is not really designed to be fast, and you need to improve the speed of roaming. And some of these standard extensions are helping with that. Now, if you want to see how roaming enhancements came along, the evolution of roaming enhancements over the last, I would say 15 to 20 years, initially there was no standards for this because the standards bodies did not really see the problem at the time. But the initial companies that were deploying enterprise networks, if you look at Cisco has been the market leader for many years in enterprise Wi-Fi, and they were facing this problem in the field because people were trying to do voice over IP calls on enterprise networks, and they were trying to roam, and they were facing these problems. So because it's a real problem for them, the industry started coming up with proprietary solutions that are specific to them, to their networks. Like Cisco came up with this CCX method, and then there are other special key mechanisms and things like that came along to make the roaming fast and secure, but they were not standards based. There was also this interesting solution from this company called Meru Networks, which basically what they try to do is they try to actually completely solve the problem of roaming by creating like a blanket network. So normal traditional Wi-Fi deployments in enterprise, you have multiple APs, and each AP is on a different channel, and each AP has could have the same SSID, but it will have a different base SSID. And so when you're roaming from one AP to the other AP, you might stay within the same SSID, but you're changing the base SSID, and so that's the station will know that it's roaming. But what if you deploy the network in such a way that all your APs are on the same channel, and every AP will advertise the same SSID and same base SSID, right? So then it's the same network. So the client, when it moves from one physical access point to another physical access point, even though it's actually moving from one physical access point to another physical access point, we have actually created a virtual network, and it's staying on the same network. It's like a VPN connection. So now the client will not know that it has moved to a different access point, because the same SSID and same BSSID are also available on the neighboring access point. And so the client never has to even roam or lose any connectivity, even though it has physically moved. It's a very interesting concept that they came along with. Unfortunately, it never got widely deployed, but that's one of the proprietary implementations that came along. And then the standards caught up, and the standards body started adding various methods to improve the whole mobility experience. So for example, the mobility experience has multiple aspects to it. It is not just about how long it takes to roam. It's also about when you decide and how you decide to roam. So there is the roam initiation part, where you have to make sure that you initiate the roam at the right time. It cannot be too soon, or it cannot be too late, right? Too soon meaning you are jumping between multiple networks continuously. Too late, which means that you're too sticky and you lose connection. So you have to make the decision at the right time. So you have to improve the roam decision process, and once you decided to roam, you have to improve the roam execution process, meaning how long it takes to roam. So both of them have to improve to actually create a better user experience. So for that, 11E had this information element QBSS, which tells how much load that you have on the current AP. So QBSS information element will say, okay, currently your AP you are connected to is 50% loaded or 60% loaded. And again, that is one factor that the station can use to say, okay, right now I'm on a very busy access point. Maybe I need to initiate a roam. And then there is faster security mechanisms, security enhancements that came a part of 11I. Then 11U came along, which helped seamless roaming between Wi-Fi and cellular, and between different Wi-Fi networks and so on. And then 11K came along, which actually really helped in speeding up the roam decision process and making it more efficient. And then 11R came along, which started speeding up the roam execution process, while 11K and 11V helped optimize the roam initiation process. 11R helped in the roam execution process, right? And that's where the whole user experience is improved as a part of these standards. Okay, so touch upon 11K a little bit. So what is the basic concept of 11K? If you take a simple example, let's say you live in a rental home right now, and you're not happy with the home, you're not getting good experience, the rent is too high, or the house is too small, or some reason you want to move to a new house. You want to check out what are the other options you have. What are the neighboring rental properties that are available in the neighborhood? So one method you can do is you can go on the road and check every home in the neighborhood. You can knock the doors of every neighbor and say, hey, is your home available for rent? Or you can go and check in the neighborhood, walk along to see if there are any for rent signs. And you can do all that work, right? And you can go to different places, and then you can shortlist, and then you can talk to all the owners, and then come up with a list of homes you want to move to. That is a long process, and it takes a lot of time. It's highly inefficient. There is a better method, and the better method is you can go to a place that already has all the information, right? For example, you can go to a rental agency or rental agency website that has already collected all this information for you. So you go to their website, you type in your requirements, you say, I need at least this size house in this area, and my rental budget is this much, and all of that. And when you type in all that, it will automatically collect all the data for you, and it will list all the homes that are available. And then you can shortlist without even moving from your house, without even stepping out. At the comfort of your own home, you can actually shortlist the homes that you want, and then select one. And then once you select one, then you go and do the connection process with them, right? So 11K works exactly the same way. And the idea here is very simple. And if you want to initiate the roaming process as a part of 11K, what the client will do is, the normal process for the client is it will go off of the channel, right? Let's say you're connected to an access point on channel 36, right? So normal process is, so okay, I need to roam now. I cannot stay connected to this current AP. So let me go off channel and scan on channel 40, channel 44, channel 48, channel 52. And in every channel, it goes and stays for a certain amount of time. And then it will scan. It will either do an active scan where it will send a probe request, or it will do a passive scan where it waits for a beacon. And you have to wait at least 100 milliseconds to see a beacon. So minimum, you have to spend 100 milliseconds on in each channel. And by the time you go through all the channels, you have spent so much time on other channels that you might lose connectivity with the current AP, and you might actually drop some traffic, because you might be actively running some application on the current channel, and that will interrupt the communication, right? So what 11K, what you can do is, the client can say, no, I don't want to go off my channel at all. I want to stay in my current channel. Instead of going and finding all the APs around, why don't I ask my current AP? So then the client will say, let me send basically a neighbor report request. So I am requesting the AP to give me a report on all the neighbors. Just like I'm going to the website of a rental agency, and I'm asking them to give me a list of all the properties that are available for rent. Same way, the client will send a neighbor report request frame to the access point, the current access point on its current channel. So the current access point will then either trigger its own search, just like the rental agency, and either it will ask the controller, if it's a controller system, and collect the information, or it will ask on the distribution system, and it will scan, and it will find all the neighboring APs. It will create a nice report, and then it will send a neighbor report response back to the access point, back to the station. And in that response, it will have all the details about all the neighboring APs. So neighboring AP1, he's on this channel, these are his capabilities, this is the BSS ID, this is SSID, and all those details, right? And once it creates a list, it sends the list in a neighbor report response. And now the client can decide, okay, I am going to get, these are my options, and this option has the best, this is my best option. So let me go connect to that access point, and then it can disconnect with the current AP and go connect to the new AP. And that is fundamentally how 11K features work. Of course, in the interest of time, I skipped a lot of things here, because 11K itself is very complicated, and it has many features to it. But the only feature that is really used is the neighbor report request. I'm going to touch on that only. So here is a packet capture of neighbor report request and response. So if you look at the response frame, it has a list of all the neighboring APs. It has basically the channel number, the PHY type, the details about each AP, what physical layer data rates it support, what signal strength you're seeing from it. All those details are available in the neighbor report. And so the client can now easily make a decision. Now, of course, as a part of 11K, it is not just about neighbor report requests. It's also about how do you optimize the channel allocation. And there are many auto channel selection mechanisms. There are many proprietary mechanisms that are implemented that are doing radio resource management. Basically, it's called auto channel selection. And in the interest of time, I'm not going to go in the detail because we don't have much time here. But basically, APs can also figure out which channel to operate in. So if I have like 10, 20 APs deployed in this building, these APs can be intelligent about what channel to use. And the goal of each one of these APs is to operate on the least congested channel. So what the AP can do is, periodically it can scan, and it can find out information about its neighbors, and it can find out information about which channel is the least busy channel. and they can rank the channels based on number of networks that are already on the channel, what kind of signal strengths, non-Wi-Fi utilization, channel bonding, channel overlap. They can use all these metrics to actually rank the different channels that are around it and pick the channel that is least congested. And periodically, access points can do this. They can actually run an ACS algorithm, and using this ACS algorithm either during boot time or at periodic intervals, it can do the scanning and it can change channels and it can find the best channel that is available. These algorithms, a lot of them are proprietary, but there are a few of them can also be standards based. Okay, so talk a little bit about that is about 11K. 11V is where, again, 11V is a very big spec, right? It's literally, I think it's about 500-600 pages long. It covers so many different features. But again, the thing that was really used, only thing that was really used in 11V is this feature called BSS Transition Management. And that's the only thing we're going to talk about right now. Is this is where the network can take control. And the network can say, I am deciding, Mr. Client, I am now deciding that you need to roam because I'm not the ideal AP for you anymore. But the signals quality is very low. And one of the problems with the signal quality being very low is, let's say if the client is at the edge of the cell on access point. What happens is when it's the edge of the cell, it normally has very low signal, which means that it will transmit at very low PHY data rates to maintain the good SNR. Remember from part 1, we talked about SNR and its relation to MCS rates and so on. So if your signal to noise ratio is very low, you transmit at very low MCS rates, which means that the same frame takes a lot more airtime. And that means it's a very inefficient use of the medium. So normally what APs will do is they will detect the clients that are at the edge of the cell, and they will know that these guys are inefficient. They're taking too much airtime. And if that client is not moving, then the AP will decide and say, I need you to move now, right? And it can basically do that. So normally how this protocol, how this works is either the client can say, I'm going to send a BSS transition management query because I want to transition from one AP to the other AP, or the AP can say, I am going to send a BTM request telling the client which AP to move to, and if the client acknowledges that, then the AP will disassociate the client. And since the client already knows where to move to already by that time, then the client will go and associate with the new AP. And this is the network's way of forcing the movement from one channel to the from one AP to the other AP. Right? So if you look at the BTM request response frames, again, if you see this particular frame here, this is the AP telling the station where to move to, right? So the AP is telling the station in the top right-hand corner here. Yeah, the AP is sending a BSS transition management request, and it is giving you a preferred candidate list, which means the list of APs that you can move to, right? So the AP is now telling, the network is now telling the station, these are the options you have. You have to move to them. This is like forced reallocation, basically. And then it's also telling that there's a dissociation imminent. So if you're not moving, I am going to disassociate you, right? Within a short amount of time. And there's also a timer, and you need to move within this time. And if you don't move within the time, then you will be disconnected, right? So that's in a nutshell how the BSS transition actually works with 11V, right? It's a network's way of forcing the roaming. Okay, so the last topic on this list was basically 11R. And so remember, to summarize 11K and 11V, 11K was helping the client reduce its off-channel scan time so that it doesn't keep scanning on all these channels and creating a lot of traffic load. And 11V is also helping the network move a misbehaving client. So both 11K and 11V, as I said before, are really helping optimize the roam initiation process or the roam decision process. So the process that is required to decide what is the optimal time to roam, when to roam, how to roam, where to roam. All these questions are answered by 11K and 11V. But once the decision is made, how can you roam efficiently, and how can you roam fast, right? And how can you roam in a secure way? That is the problem that 11R is trying to address. Okay, so 11R really introduces a concept where a lot of the initial handshakes with the new AP can be avoided. So if you look at a standard .1x connection process, when the station connects to an AP, it will go through the full process of authentication, association. Then there is a .1x exchange. Then we exchange certificates. Then we generate session keys. Then we generate the four-way handshake, and then we start encrypting the data. So all of the process happens when you connect to the AP for the first time. What 11R allows you to do is to avoid all those steps when we move to the new AP, right? And it actually transfers the key context, the security context, from the current AP to the new AP without the station having to worry about it. So if the station connects to a current AP and it has to create a secure connection, then it has to build the context, security context. If the station has to connect to the new AP, and if it has to start from scratch, then it has to build the security context all over again. So if you want to avoid that, the current AP can move the security context or the security information of that particular station from the current AP to the new AP. And if the AP is able to do that, then the station doesn't have to establish new connection with the new AP. It's just like when you are going to a new place, if someone has already told someone else in the new place and they've already introduced you there, then you don't have to introduce yourself again, right? They already know you, they know who you are and all of that, and it becomes easy, right? So it's the same concept where 11R allows you to move the security context through the network so that the station doesn't have to reestablish the security context, basically. So for 11R, there are two common methods that are used. One is called basically over the DS, and another one is over the air. Those are the two methods that are listed here. So you can see, I'm not going to go into all the details here, but basically to kind of summarize it in a simple way, over the air really means that the station will connect to the current AP, and then it will advertise its capabilities that it is 11R capable. The AP also will advertise it's 11R capable. It creates a security context with the current AP, and then when it moves to the new AP, it doesn't have to do the full exchange, because as a part of the authentication request itself, it can provide all the key information, right? So when the station is trying to connect to the new AP, the .11 authentication request will have all the information elements, the other security elements that are required. And then the authentication frame itself is used as a way to exchange the security context over the air. And once that is done, then it's just a matter of doing a reassociation. So then the station can reassociate with the target AP. And then once it gets a response, now it has a secure connection with the target AP. And it had avoided all the entire .1x connection process, key exchange process, and all of that. So this is how the over the air works. Over the DS is where basically the station will send a special action frame to the current AP, and then that information, that security and then the action frame has a security context, and then the security context is moved from the current AP to the new AP over the distribution system, over the wired network, right? And then that information is sent to the new AP, and then the new AP will respond back to the current AP over the wired network, and the current AP will respond to the station. And then once that exchange happens, then you do a normal reassociation with the new AP, and then you have a secure connection going on with the new AP. Of course, I'm not going through all the details here, just in the interest of time. But we have some references where you can go, and there are more detailed references available. Lots of really nice videos available that explain these things in a lot of detail. For those of you who are interested, you can certainly look at those references. I'm trying to cover a lot of ground in a small session. I hope it's not too confusing, but that's mostly what 11R is about. Okay, so here are some references from today's session, and just to summarize what we have covered, we looked at basically DFS, how DFS works, and how this how the regulatory bodies require you to pass DFS certification, how you can effectively use the DFS channel without by following all the rules. We talked about that. We talked about auto channel selection. We talked about the ROM initiation, improvements in 11K, 11B, and then ROM execution. We talked about 11R and so on. Right. Still have a couple of minutes, so maybe I can show a quick packet capture here. So you can see from this particular packet capture that this is 11-hour packet capture. So here you can see that initially the client associated with a normal process. So the client is connecting to AP1. It is doing probing, authentication, association. Then there is a whole EP exchange, certificate exchange, client hello, server hello. And from after the certificates are exchanged, then you do the four-way handshake, and then all of those things are done, right? And once all of these things are done, and this is when the client is connecting to a particular access point here. So the client in this case is connecting to basically edge core 46B1, the last 2 bytes of the MAC address. It's initially connecting to the first AP, 46B1. But now when it wants to move to the new AP, which is basically 472E, which is a new AP, now when it connects to the new AP, basically it's just doing an action frame. In this case, this one is doing over the DS. So it's basically sending an action frame, and it is doing a fast BSS transition. It's exchanging the information about the security context, the MIC, the anons, the SNONs, and all the PMK information. Everything is exchanged, sent ahead of time to the new AP. And then once this action frame exchange is done, then the client, which is CompX, is the client which is connecting to the edge core AP, is just basically doing a reassociation, right? And then there's a reassociation request response, and after that, successfully, you'll start sending data. So there is no repetition of all the certificate handshakes, the four-way handshakes, and all of that. And it's a simple, straightforward process here, and it speeds up the roaming. And in our testing, especially when we have seen there's a huge improvement with 11R, and most of the testing that at least I have done, basically 11R roaming is much faster than the traditional roaming. And it's especially when you're doing voice traffic and other kinds of things, it becomes especially more important, right? So this is 11K capture, but again, we'll put it in the notes. We don't have time to cover that, but we'll also attach all these capture files as well for you to look at of how neighbor report requests and BTM requests, response frames, all of them look like, what the information elements are. We can post that in the references section. So that is today's session. Hopefully you found it useful.